All right. So, afternoon, everybody. So, first, I want to thank Abu for doing a really nice lecture in the last class. I like to hand over a lecture or three to my TAs every semester. I'm not just teaching them to, you know, conduct office hours. There's also this business of training them to actually be instructors. And some of them do a much better job than others, and Abu is just outstanding. So that's the good news. The better news is that he'll be doing a couple more classes because I'm going to be gone most all of next month. Uh, our classes will be on Zoom starting next week, except for the lectures on GANs, which Abu will conduct here in person. I'm going to be gone to Italy for a conference, and then after that, I'm going to go to India for a conference. I have a gap in between. That doesn't make sense for me to come back and go. So I'm finding a place to host me for the intervening 2 weeks. So by the time I'm back, your semester will essentially be over. That said, I'm going to be available on Zoom and email, and I will be in contact. It's just that I won't be here in the classroom, right, or in my office. And why is the class so empty? This is what happens in the last fortnight of April. When it begins happening before April begins, then, all right, so let's begin. We're going to be talking about representations. We went through all the basic ideas. What are neural networks? How do we train them? We learned all about MLPs. We learned about convolutional neural networks, recurrent neural networks, sequence-to-sequence formalisms. We saw a bit of how the sequence-to-sequence formalisms take off and go become things like transformers and so on, which power most of LLMs and a lot of the AI you see today. In the next sequence of lectures, we're going to learn a little more along those directions. But today we're going to learn the basic idea what do neural networks actually try to do with your data. We know the outcome. They perform classification. They perform prediction. What happens in between, right? So neural networks are universal approximators. They can model any Boolean, categorical, or real-valued function. They can check for static patterns, like in MLPs. They can scan for patterns. They can analyze time series. They must be trained to make their predictions. What happens internally? Now, here's the basic problem of learning in a neural network. You're given a collection of input-output pairs, shown by those lines. We've seen this picture several times before. And we must learn the function that these measurements have been taken from. So if you had a classification problem, you're going to have data of this kind. Again, this picture is familiar. Let's say you want to learn the double pentagon decision boundary. Then you're going to have training samples, some within the class boundary, some outside. So the red dots represent data instances within the class boundary. The blue dots represent the training instances outside the class boundary. And from these training data, you must actually learn this function out here, which is the double pentagon. I'm not a very good artist. Otherwise, the double pentagon would look nicer. Now, in reality, this is not the kind of data you're actually going to see. You're not going to see these pretty data where all the data within the class boundary belong to one class and all the data outside the class boundary belong to the other class. Data tend to be fuzzy. So it's not possible. This picture is essentially the same as this one with a little bit of noise added in. But if you looked at this, there's no way you're going to tell me this is a double pentagon decision boundary. And yet from data of this kind, it must learn to do the job. So just translating that to a linear classification problem. Now, in a linear classification problem, which you can model using just a single perceptron. Remember, again, a perceptron is a linear classifier. You are computing an affine function of the inputs. You're applying a monotonic activation to it. And then the output of this activation will be compared to a threshold, which means that you're really comparing the input affine value itself to a threshold, because a monotonic function doesn't change the boundaries, right? And the boundary is going to be a hyperplane. So the actual function that you're learning is going to look like a step function. Now, in this case, you're trying to learn something like that red function, but the data that you would see would have some red dots flying in the air on the blue side, some blue dots lying on the floor on the red side. And from this data, you have to learn the boundary. Or if I go back to an even simpler problem, a one-dimensional problem, this is the kind of data that you're going to see. Red dots, blue dots. Red dots belong to class 1. The blue dots belong to class 0. And from these data, you're going to have to learn a function which learns to classify the red dots from the blue dots. Now, it's clear that what's happening is that you're going from the blue side to the red side as you go from the left to the right. But you have red dots on the blue side and blue dots on the red side. And if I just threw this at the neural network, it can learn a function of this kind, because we know that a neural network is a universal function. It can learn pretty much anything. You give it enough capacity, it can learn this function, right? Is this really what we want to learn? Now, you might say yes, but let me give you a tougher problem. Suppose I've got something of this kind where I have the same value of the input but different labels. So here, for example, yes, Denise. Thank you. Thank you. Yes. I can't teach you that my scepter, right? So let's say I have data of this kind where I have red dots and blue dots at the same X location. So I have data instances with the same input value and different class values, right? And just for a hypothetical example, let's say I have 100 training instances with the exact same input value, but 90 of them have class label 1 and 10 of them have class label 0. What must the ideal output of the network be? Do you want it to output a 1 because the majority are class 1? Or would you rather input the value 0.9, which tells me that 90% of the data with this value of X are class 1? Which one would make more sense? 0.9, because it's more informative, right? It's telling you that some things can also belong to the other class. But what is that number? What does 0.9 really tell us? 0.9 is our estimate of the probability that if I took a random data instance whose input value was exactly that X, what is the probability that that instance would belong to class 1? Of all the data instances which take that value X, 90% of the data instances belong to class 1. So if I randomly chose a data instance from that set, 0.9 of the time, they're going to belong to class 1. So this is the probability of one given X, right? So it clearly makes sense. This makes more sense for us to be outputting. But then let me change things a little bit. I perturb my collection of 100 data instances. So they're all fractionally off, 10 raised to minus 16 off the limit of your floating point precision, right? They're not exactly the same X. Did the situation change so much that now I suddenly want things to go up and down and capture every instance individually? Or does it still make sense for me to say 0.9? What would make more sense? 0.9, right? How much can I begin spreading these before you say it's no longer 0.9? If I begin perturbing them and they begin spreading out, at which point would you say this doesn't make sense? At this point, it's something changed, right? But the same logic still holds. And so let's go back and look at the world from a completely different perspective. At each input X, let me look at a little window shown by the oval window of inputs around that region. And my output is going to be the fraction of instances that belong to class 1 within that window. So as I slide the window from left to right, initially I'm going to see all blues. So Lakshya, there's coffee outside. All right. The perils of sleeping in my class. Go ahead. All right. Anyway, there's As I slide from the left to the right, initially all the instances belong to class 1, so the fraction is going to be, all the instances belong to class 0, so the fraction is going to be 0. As I keep sliding out front, that fraction keeps changing, and eventually you're going to see all class 1s. So as I look at count fractions within a window, this is the kind of relationship you're actually going to see. So this is what you'd want your network to actually capture, right? What is an immediate question you would like to ask me when I give you this logic? What is the width of my window, right? I mean, how did I magically decide that? I'm not going to do it. So this is where I'm going to slide into statistics. And it turns out neural networks are actually statistical machines. They don't mechanically compute things, they actually compute probabilities. So this is the shape of the curve we saw, and that curve is very nicely captured by the logistic function. And the logistic function, as we all know, is 1 over 1 plus e raised to some minus z, right? And what happens if z is a very large negative number? What happens? For z is a very large negative number, this is going to become 1 over 1 plus e raised to minus of minus z, which is going to be 1 over 1 plus e raised to z, which is 1 over infinity, which is 0, right? So as z becomes a very large negative number, this value becomes 0. As z becomes a very large positive number, what happens?
It becomes 1.
It becomes 1. E raised to minus z it becomes 0, right? So 1 over 1 plus e raised to minus z becomes 0. And in between, it's continuous. And that's why you have this nice shape. And so it turns out that the logistic regression actually models the a posteriori probability of class 1, the probability that the class of the instance is 1, given that the input is x, right? And so the logistic perceptron, which is just 1 over 1 plus e raised to minus w0 plus w1x, which we've seen, is just capturing this logistic function, which models the a posteriori probability of class 1 given the input. Now, this is for a single input. If I went to 2 inputs, 2-dimensional space, again, in the 2-dimensional space, your data are going to look like this: red dots on the blue side, blue dots on the red side. There's no hyperplane or line that cleanly separates the red from the blue. And so if I had to put a function there, you'd want a function, a sheet, which looks like the sigmoid. In the 1-dimensional case, it was just a nice sigmoidal curve. Now imagine me taking a piece of paper, and there's an imaginary piece of paper, and I've imaginarily sort of folded it into a snake-like curve, right? And I'm rotating it to fit give you the boundary. So this is what you really want to model. And in fact, your logistic perceptron with 2 inputs is going to model this shape. This is going to be, you're going to get the same sigmoidal curve surface in any number of dimensions as you increase the dimensionality. But in every case, it is actually modeling p of y equals 1 given x. So here it is, right? This function is now modeling p of y equals 1 given x. You ask me a question: what's the width of the window? I'm going to punt on the problem. Instead, I'm going to look at it from a purely statistical perspective. This is for matters of convenience. I'm no longer going to use y equals 0 and y equals 1 as my labels. I'm going to use y equals minus 1 and y equals plus 1 as my labels. Nothing really changed. I just use a different numeric designation of the 2 classes, right? So this is p of y equals, this is your standard logistic function. And this models p of y equals 1 given x, right? What is p of y equals minus 1 given x? What would it be? Where, Thomas? Why do you ask, is it? Why would you not be 100% sure? Is there a third outcome? No, right? So I have only 2 outcomes: y equals plus 1 or y equals minus 1. So if this is the probability of y equals 1 given x, the probability of y equals minus 1 given x is going to be 1 minus this guy. What would the formula for that be?
It will just be this e to the power minus z upon the same denominator.
How did I magically manage to lose my chalk? They have feet. I hate chalks. Okay. Does anybody see my chalk? I'm going to look. Sorry, guys. This is empty. Turns out all of these chalks walk, all professors suffer the same disease, walking chalk syndrome. Anyways, so I have 1 over 1 plus e raised to minus z equals p of y equals 1 given x, z in this case. So 1 minus 1 over e raised to minus z is going to be 1 plus e raised to minus z minus 1 over 1 plus e raised to minus z. These will cancel away, and I can multiply the numerator and denominator by e raised to z, right? And this is simply going to become 1 over 1 plus e raised to z. So the only thing that changed is instead of being e raised to minus z, it became e raised to plus z. Now, this is p of y equals minus 1 given z. Can you give me a common formula that links these two guys? Can you give me a common formula that links these two guys?
Y times z.
It's going to be y times z, right? Because of note over here that the sign of this guy and this over here, they're just inverted, right? So I can just write it as p of y given x equals 1 over 1 plus e raised to minus of y times w0 plus w1x, right? Everyone with me? Okay. And so here's what I'm going to do. Suppose I'm given a collection of training data, lots of xy pairs. X's are vectors, y's are binary plus 1 minus 1 labels. Now the total probability of the data, assuming all of these are independent, is going to be the product of the probability of the individual instances, right? Which I can write as, I was scared. I thought even this had worked. Okay, so I can just decompose this as p of x times p of y given x. I can separate that out, and p of y given x, we just saw, was this guy here, right? So I can plug it in. So it's the product over all training instances of the probability of x, which is the input, times the logistic function computed at that x and that y. Everyone with me? Right. And I can take, I've just repeated that on the top. I can separate out the x portion of it and the y given x portion of it, as I have in the second line. And now I can take logs. And what is the log of the probability of my training data? It turns out that that's just the sum over all of the training instances of the log of p of x plus the sum over all training instances of the log of the logistic function computed at that y and x. Now, which of these two terms depends on the parameters of the function?
Right.
The one to the right, right? So that's the only one that I need to estimate. And now, here's a basic principle in statistics. There's the principle of maximum likelihood estimation. The principle of maximum likelihood estimation works on the solid hypothesis that the world is tremendously boring. It's so boring that everything you see is very typical. Anytime you come to a classroom, you're going to see a smattering of students because that's what you see in classrooms, right? In fact, I'm going to see you guys. Now, if I work with that hypothesis, then if I give you a large number of models, and I say which of these models best explains this data, you are going to choose the model for which these data are most typical, right? And so the principle says if I have a lot of these models, which I have, I can define a probability distribution of p of x semicolon theta. These are the parameters, right? And this is the random variable. And so I have a lot of models. I have p of x semicolon theta 1, p of x semicolon theta 2, and so on. Which of all of these explains my data best? It's going to be the one which assigns the largest probability to my data instances, all the data that I've seen. because that's what makes these data most typical, right? And so your maximum likelihood principle says that if you have a parametric distribution P of x semicolon theta for any random variable, then theta is going to be argmax. My best guess for theta is going to be argmax over theta of basically you're saying that whichever theta assigns the largest log probability, or alternately the largest probability to whatever I have observed, that is the theta I'm going to assume is what really represents my distribution. Again, this is all based on the principle that what you observed is typical. The world's very boring. Nothing unusual ever happens. If your data violates that principle, your model is going to be off. So using that maximum likelihood estimation principle over here, I can say that my best guess for W0 and W1, remember this is a probability model, right? Is going to be the one that maximizes the log-like probability of the training data. In other words, because the P of x doesn't depend on W0 and W1, I can ignore this. So it's going to be the W0 and W1 that maximize the log, the sum of the log of the logistic function computed at each training instance. And as it turns out, maximizing this log likelihood is the same as minimizing the negative log likelihood, right? And what is the negative log likelihood? It just turns out that this is exactly the same as the Kullback-Leibler divergence between the actual labels and the output of a logistic function. The output of a logistic function doesn't have y in it, right? So this is just the Kullback-Leibler divergence between the output of the logistic function and the actual labels. So when you train your models to minimize the cross entropy or the KL divergence, you're actually training your models to make a maximum likelihood prediction of the probability of y of the label assigned to each training instance. This is a maximum likelihood estimator. Everybody with me so far? Any questions? Yeah.
If you add regularization techniques, is it still MLE?
So adding, it actually becomes, at that point, it's not strictly MLE, but it's actually maximum a posteriori estimation because your regularizer, again, can be explained as a prior on the parameters. So it's MAP as opposed to MLE. That's about it. Yeah.
So, Professor, what do you exactly mean by a posteriori distribution?
You've seen Y, you have seen X over here. Wait. Let me, what is this term? This, before you see X, you're going to say 50% of coin tosses are heads, right? Then I see a little bit of the face of the coin. Maybe someone gives you a partial coin. Based on that, your guess for whether this is a heads or not is going to change. You're not going to assign a probability of 0.5. It will be something else, right? So that is posterior to having made an observation. And so an a posteriori distribution is the probability you assign to the label, to the random variable after posterior to having observed something about it. So this is the a posteriori probability of y given x. Okay. Right? Now, so what we're good so far, right? Now, but what about this guy? Everything that we spoke of was about linear classifiers. What happens with nonlinear classifiers? You have this crazy problem. You have data, and you're supposed to learn a boundary. And maybe you have data which is kind of fuzzily separated, so you can't really draw a clean boundary. It's kind of painful to deal with this, so let me just go back and regress to the simpler problem where my boundaries can be cleanly drawn, right? Now, what do we know about the perceptron? What kind of a classifier is the perceptron? What is the kind of boundary it gives you? Linear. Linear, thank you, right? Is this boundary linear?
No.
No, so we have a problem, right? Now, suppose I have a sufficient net. We know we can exactly model this. Oh, wait, my chalk is here. Now, suppose we know that we can exactly model this decision boundary using the network that I've shown. I have two subnets, each of which computes one pentagon. And then I can OR the two, right? Now, over here, that final neuron is a linear classifier. It can only draw linear decision boundaries, right? Linear decision boundaries in what? What do you think these two neurons are outputting? In the space of the output of those two neurons, what will the boundary be like? It's got to be linear because the final classifier is a linear classifier, right? And so if I looked at the y1, y2 space, in the y1, y2 space, the boundary must be linear. The fact that I can actually draw a perfect, I can train a perfect classifier which perfectly separates one class from the other means that in the y1, y2 space, those classes are linearly separable. And that's why my final neuron is able to train a classifier which perfectly separates the red from the blue, right? So then what is this guy doing? Yeah.
We're projecting effectively like the data points into another coordinate system, right? It's a projection operation sort of.
Yes, but what is the property?
Property.
So what this box does is basically a transformation that transforms your data bit by bit until the classes become linearly separable. And so the network actually has two distinct components. The lower component, everything until the classification layer. You can think of that as a feature extraction or a feature extraction component, which extracts features that are linearly separable from the data. It transforms the data. It doesn't, in the beginning, it doesn't matter how horribly the data are distributed. The network is moving the data, shifting it around till it's segregated in a manner where the classes are linearly separable. That's when the final neuron can actually do a linear classification job. And this is going to be true not just of a perfect network structure, right? This is going to be true of any sufficient structure. If the structure of my network permits the network to classify my data exactly, then my network is going to, then what this means is that when the network is trained, the lower portion of the network is basically transforming my data such that the classes are linearly separable. And then the upper portion is, and then you have the final classification layer. So again, here I'm showing you a binary classification problem. What would a linear classifier be when you have a multi-class problem? What's it going to be? Can anyone tell me? Yes.
Oh, no.
Yeah.
So in
Huh? A plane, no, but I have many classes, right? Yeah.
So if you can do a one versus many, like you create multiple sort of.
Yeah. It's about.
we can have multiple classifiers where, as you mentioned, one versus many, where we can assume, okay, all of these are like if you have multiple types of flowers.
So yeah, what this means is that regardless of which pair of classes I take, I can draw a decision boundary that's a line between the two, right? So based on this, what assumption can you make about the decision region for individual classes?
Interclasses are linearly separable.
All the classes, individual classes are linearly separable. So what would the actual decision boundaries for the individual classes be? You're going to say, let's say I have C1, C2, C3. Then I have one decision boundary of this kind because C1 and C2 can be linearly separated, right? I have one decision boundary of this kind because C3 and C2 can be linearly separated. I have one decision boundary of this kind because C1 and C3 are going to be linearly separated, right? And that tells me that C1 is this region, C2 is this region, and C3 is this region. That's the kind of boundary you're actually going to see. That make sense?
Yeah.
Right? So if you actually plotted TSNE plots for your final features, very often, you're going to find that if you plot the various classes in your space, you're going to find that the decision boundaries that separate the different classes have a radial pattern. It doesn't have to be radial, but you get the idea how the whole thing works, right? You can just get Voronoi buckets for each class, which is a convex polytope as well. Now, hold on. And that is in the feature space. After the features have been computed, if you plot the decision boundaries in the feature space, that's where it's going to be linear. Okay, this one was easy. 10 seconds, guys. Time's up. Somebody on Zoom want to take the first question?
True.
Second, here, Lihan.
Oh, true.
Okay. All right. If I see you poking with your phone, I'll ask you a question, right? Keep your phones folded and put them in your pocket. Now, the portion of the network until the second to last layer is the feature extractor, which extracts linearly separable features for the classes. And the output layer is a linear classifier that can only perform well if the rest of the network successfully transforms the input space, just swaps it such that the classes are linearly separable, right? And when the data are not linearly separable, so you have fuzzy boundaries, the boundaries are not linear, which is what happens, which is more typical for classification problems, then what do we have? The feature extraction layer is still going to try to transform the data such that the posterior probability may now be modeled by a logistic. Because the output, typically our output neuron has got a softmax or a logistic function, right? And a softmax is basically just a multi-class generalization of a logistic. And so the logistic function is going to try to draw linear decision boundaries of this kind. The softmax is going to try to draw linear decision boundaries of this kind. This is all it can model. And so this means the rest of the network must push the data around such that the classes are linearly separable. Again, it doesn't always have to be radial. It just has to be, every class will have a convex boundary. Convex polytope is a boundary, okay? And because the data may not be separable, it's going to try to, and because the output layer is a logistic function, the rest of the network is trying to move the data around such that the classes, in the feature space, the classes can be well modeled by a logistic function. And so when you have inseparable classes like that kind, with an output, just going back again just to the linear case, when you go to the linear case and you have inseparable classes, then we know that the output, the function is, the logistic function actually computes the posterior probability, right? But then the output neuron is now no longer working on the data. I can think of this gray box as some function f of x, which is extracting some features from the input space, right? So at this point, the output neuron is actually working on f of x. It's computing p of y given f of x, right? And because the function that we have is typically going to be it may not even be many to one, it's often just 1 to 1. So in that case, because the network is a fairly complex thing, so there's a correspondence between x and y. So p of y given f of x is going to be the same as p of y given x. And so as it turns out that the network, once I have a logistic function on the outside, and I think of the rest of the network as extracting features from the data, the network, the entire network is just modeling p of y given x. It's modeling the a posteriori probability of the class given the input data. Except it's a very complicated distribution, right? It changes very rapidly with x. Again, this is not going to integrate to 1 over x because x is on the conditional side. At any given x, the probabilities of all the y's will sum to 1. And the model is actually learning p of y given x. Is that making sense? Right? For every data, this is what it's going to be learning. And so the output of the network is always p of y given x. For a multi-class network, it's going to be the vector of a posteriori class probabilities. And if you train this to minimize the KL divergence between the output of the network and the target output, what you are really doing is performing maximum likelihood training of the entire network. You're modeling, the network is modeling P of y given x. And we saw that minimizing the cross entropy is the same as maximizing the log likelihood for an individual perceptron. But the fact that the rest of the network is extracting a feature did not change this interpretation, right? And so overall, when you train this network, you're actually performing maximum likelihood training of a statistical machine which computes the a posteriori probability of classes given the input. Questions? Did it go clean over your head or just partially over your head? Yes.
So when the boundary is not linearly separable, like the data that is shown here, like that network would not technically be sufficient to create a proper boundary, right? So does it just do the best shot at whatever?
So it's doing a maximum likelihood estimation of a parametric model, right? It just means that the parametric model is insufficient to model this distribution perfectly. That's it.
So it'll still try to maximize the.
It's still doing a maximum likelihood training, right? Yeah.
Not visible.
That was too quick.
It says
Professor, the
cannot be found.
Cannot be found.
There it is.
Okay, release all the poles.
No, I didn't see it. Oh, yeah.
If it beeps once more, then you're done. Okay, go ahead, Giovanni.
Could you repeat the point that you made about the fact that probably they do not sum up to 1?
So P of y given x sums to 1 over y's, not over x's.
Okay.
That's all, right? So, all right, time's up, guys. Someone on Zoom, is that first statement true? Zoom?
Yes. Yes.
Second one. Is it true?
Yes.
Third? No? Okay, and what about the fourth, Giovanni?
No.
Wait, why is my... Okay, here's what. Yeah, here's the crazy thing. The classification neural network is just a statistical model that computes the a posteriori probability of classes given the inputs. This is what we just saw. Training the network to minimize the KL divergence is the same as maximum likelihood training of the network. By the way, if you're training the network using any other laws, you're still training a statistical model. The model is still going to try to compute P of y given x. It's just that your training paradigm is no longer maximum likelihood. You're using some other mechanism, right? The training the network by minimizing the KL divergence gives us a maximum likelihood of the network parameters only when the classes are separable. No, this has nothing to do with the separability of the classes. The last point is interesting. The training of the network is basically extracting features that are linearly separable, right? Or maximally linearly separable. Once you learn a feature extractor of this kind, you can throw away the classification layer. And now you have a feature extraction module. And then you can use that to extract features and learn any other kind of classifier. This is the basic principle of transfer learning, right? So you learn on something, you use the feature extractor on something else. That's because this network, the lower network, is actually learning to compute linearly separable features. Right? And so the story so far, a classification MLP actually comprises two components, a feature extraction network that converts the inputs into linearly separable classes or nearly linearly separable classes, and a final linear classifier that operates on the linearly separable features. Using a softmax, the final layer of the network actually computes a posteriori probabilities of the classes. So training the network to minimize scale divergences is identical to maximum likelihood training of the network. So we saw what happens at the penultimate layer, y1, y2. What happens below that? Let me keep going down, right? Trying to understand what the network is doing at each stage. Now they too compute features, right? But what do these features look like? Can we take a guess? It turns out, if you look at it carefully, what the network really does is to begin shifting the data around to increase the linear separability between classes. So as the data proceeds through the network, they become, can you shut your laptop? Yeah. Not this way, the other way. Oh, just looking at the slides, all right. Okay, fine. So what do I do? Anyways, so the hypothesis here, which can be substantiated with some math, is that as the data go through the network, they actually become increasingly linearly separable, but it's not so easy, right? Something is not so, you have to sort of think about it. You have to be a little careful in your interpretation. So here is a very simple problem. I'm trying to train a classifier which can learn that circular decision boundary. Everything inside the circle is a 1, everything outside is a 0. I'm using the dots as my training data, right? Now, this network has only one hidden layer. It has 3 tanh neurons, right? But then if you look at what is happening, if I write the math out, in the first step, let's say I have some input. So this is a 2-dimensional input. I can represent my 2-dimensional input as some plane, which I'm representing as a square, right? Then this is being multiplied. So this is my space of X. This is being multiplied by a 3x2 matrix to give me something else, right? I'll call this Z. What is the dimensionality of Z? If I multiplied 2-dimensional vectors by a 3x2 matrix, because that is the weight matrix, right? What is the dimensionality of Z? 3, right? So this Z is going to be in a 3-dimensional space, correct? But are the data going to occupy all 3 dimensions?
No, not necessarily.
What do you mean not necessarily? Guys, you are in the masters and PhDs programs at CMU. I'm asking you what happens when I perform a linear transformation of 2-dimensional data into 3-dimensional space. What does this? Do the data occupy the space?
It might be it's just a simple plane.
Go ahead, Yutian.
It only occupies a linear subspace.
It only you have not added a dimension to the data itself. There is no variation along a 3rd dimension, right? So the data are going to live along some 2-dimensional plane in this 3-dimensional space. And it's a plane because the transformation is linear, W times X, right? Now, I apply a nonlinear transform to the data, right? What happens?
Makes use of the dimension.
Now it makes use of the dimension. This plane is going to get warped. It's going to get warped, and it's going to take, instead of just being a plane, my activation function is going to convert it to some surface. It's going to be a 2-dimensional surface. It's like a folding of a plane into a nonlinear surface, correct? But then for the final classifier, I'm multiplying it now by a 1x3 matrix, right? What happens now?
It tries to condense it back to 1 dimension.
What happens now?
It tries to
That is going to be, the W is going to be some vector here, correct? And this operation is going to project everything onto the W, right? And so now on this, now we are going to have a 1-dimensional representation. And the 1-dimensional representation, you're going to have that plane occupy some region of this line. That makes sense to everybody? Because when I project this down, this is the only region in which the projections are going to fall, correct?
Okay. Yeah.
So it's going to occupy some, and now I finally put a threshold, right? If I put a threshold on it, what I'm saying is, here is a threshold. On this line, when I project everything down, everything on this side is going to be a 1, and everything is on this side is going to be a 0, or vice versa, right? You see what is happening over here, step by step. And so this means that when I train my model, what must happen is, first, my first weight matrix must somehow take my two-dimensional space and align it in a correct plane in three-dimensional space. Then, and what must the characteristic of this be? The characteristic of this must be such that when I warp it using the activation function, then all the data, so here, for example, if this is my positive class, if I warp it using my activation function, this region is going to be what represents the region inside the circle, right? And then when I project it down, if I find, so that's the first thing that I need to do. And then when I project it down, if I find the right W to project it onto, then the blue regions will cleanly separate out from the red regions. That making sense?
Yeah.
Right? And so here's what the training really does. If I can find my mouse, you can see how, on the left-hand side, you can see how it's searching through the two-dimensional planes in three-dimensional space. That is what searching through the W's is doing. The second picture shows you what happens after it has been warped using the tanh. The third picture shows you what happens when the whole thing has been projected down onto the line. And then when I find the optimal threshold, that's the actual activation function, decision boundary that you're finding. So you can see what's happening as you go through the network. It's searching for the appropriate representation, moving planes around such that when things are warped, when that plane is warped into a nonlinear surface, the classes are linearly separable, right? Is that making sense, right? It's very nice. As a visualization, this is kind of cute. It really tells you what's happening. Here you go again. You can see how it's searching for stuff and plotting it, yeah.
This is a great visualization, Professor.
Yeah.
Can we, for all possible decision boundaries, if by adding another dimension, convert it into a linearly separable case?
Not necessarily. So here, let's move on, right? What happens if I have more classes? This visualization kind of tells you what happens. But you can't do this in one shot. We have to stage it, right? And so what happens as you go through the layers is that each layer is going to try to position things such that they are linearly separable, but it's not going to succeed. And so as you go through the layers, the data are going to become increasingly linearly separable. This is from CIFAR. This is a 11-layer network, I believe. And so the top left corner is the accuracy of the classifier. And this is a high dimensional data set, but we projected the representations down to 2 for visualization. And you can, and the colors represent the classes. And you can see it's too fast, but you can see what happens, right? As it goes through, it jitters it around and separates the classes. At each stage, the classes are somewhat more linearly separable than at the previous stage, right? And this maybe is not the best representation. So let me try showing you a projection into 3 dimensions. And you can see how, as it goes through the network, the classes become more and more separable. And here's the crazy bit. The classes are already linearly separable by layer 9. The final 3 layers, when it's properly learned, are not really doing very much, right? Maybe they're increasing the spacing between classes, but even if you didn't have those, after training the network, if you threw away the last 3 layers and then stuck on a linear classifier at the end of it, it's going to learn the classifier to classify the data just fine. And in fact, that may sometimes be more generalizable than the classifier that you get at the end of the entire network. Yes. Someone raise a hand. Yeah.
So, Professor, is this sequential where the weights are applied to Z first, then it goes to higher dimension?
So this is the architecture of the network is, I think we actually used a cylindrical network, but regardless, this is what would happen, yeah.
So do we not require, if we have n different classes, n plus one dimensions to basically?
Can I separate 500 classes using a single line? I can. I just put them in 500 different regions of the line. Right, but I've projected this down to 3 dimensions for visualization. The actual dimensionality is much higher. Yeah.
So Professor, then can we say that given a complex net that can model, we can separate anything to be in linearly separable classes?
That's what it's supposed to be doing especially when you overfit. That's basically what happens, right? Because the final classifier is a linear classifier. Yes.
So the complexity of the network or adding more layers means that it's more likely to overfit.
There's, at some sense, no, it's more likely to increase the margin between classes, but then it also depends on the size of the classes, the regularizations you apply. So
Right.
it's a more complex question than you're asking, but yes, at some level that is the truth. Okay. So questions, anybody? Yeah.
Is this why using wider networks are beneficial because it can project to
Higher dimensional spaces, yes, exactly. So we sort of looked into what the network is actually doing inside. But then let's change gears a bit, right? We've seen that the network learns there. We've seen what it learns below. Let me go further down, right? We've seen what happens to the data as it goes through the network. But let me look at the very first layer just for the joy of it, right? Let's consider a single perceptron, and I'm going to be looking at your standard threshold-based perceptron, just because it makes interpretation kind of simpler, right? You're looking at a weighted sum of inputs. If the weighted sum exceeds a threshold, then perceptron fires, otherwise it doesn't fire. If I write it in vector format, right? My inputs now can be represented as a vector. I can take all of these x's and represent them as a vector x. I can write all the weights w as a vector out as a vector w. So the weighted sum of inputs is simply the inner product between the input vector and the weight vector. And this perceptron fires if this inner product is greater than a threshold. So Evan, what can you tell me about the relationship between the two vectors? Geometrically, what does this mean? What does the inner product between two vectors quantify? Let's say both vectors are the same length. Suppose both vectors are the same length. Is the distance? The angle, right? So here's a shocking fact. All vectors are the same length, more or less. You don't believe me? You have to. In high dimensions, so where does the mass, the majority of the volume of a sphere lie, of a hypersphere? It lies close to the surface. As you keep increasing the dimensionality of the sphere, more and more and more and more of the volume lies close to the surface of the sphere. By the time you get to 700 dimensions or 1 million dimensions, basically the entire data lie on the surface of the sphere. When you begin visually inspecting things, you're always pulling out outliers, like let me look at all zeros and a single 0.5. No, if you just pulled a random data vector out of the collection, they're all going to be more or less the same length. So as far as I'm concerned, all the x's are the same length, right? Which means I have a w, and I have an x, and the lengths are fixed. Now, when the lengths are fixed, when I say x transpose w, the inner product between x and w is greater than theta, I can ignore the lengths. The inner product between two vectors is the length of the first vector times the length of the second vector times the cosine, right? The lengths are immaterial. So you're basically saying that this guy fires if cos theta is greater than some value, threshold divided by the lengths. In other words, the network fire, the perceptron fires if, when is cos theta greater than some value? When the angle is less than a value, right? So the perceptron fires when the angle between the weight vector and the input goes below a threshold. So in other words, you can think of the weight vector as a template that the perceptron is searching for. And anytime the input is closer to the template than some threshold, it's going to fire. That makes sense to everybody? Yeah.
So the weight vector is like an ideal y equal to 1 example.
Yeah, if you have just a single perceptron, right? So now this means, suppose I wanted to build, I had this, you've seen these old LED watches, right? They have these ugly LEDs. Suppose I wanted to build an automatic system which looked at these patterns and decided if it was a 2 or not, had to decide if it was a 2 or not. I didn't have to do anything fancy. All I had to do was to set my weight pattern to be in the shape of a 2 and compute the inner product between my inputs and the weight pattern. The inner product between two vectors is basically the correlation between the input and the weight pattern. If the correlation is smaller than some threshold, I say, nah, they don't match. If it exceeds the threshold, it matches. So the perceptron is looking for specific patterns, right? And so now this leads me to this next thing. When I train my classifier, the first layer neurons are all basically just looking for specific patterns. And which patterns are they looking for? What is the pattern they're looking for?
Which can be separated.
They're basically looking for the pattern represented by their weights. Correct? Every single neuron says, every single perceptron has some pattern. It says if the input matches my pattern, I'm going to fire. Otherwise, I'm not going to fire. So if I trained a classifier to just look at these LED patterns and decide if they are digits or not, they'll fire, right? Every one of those, the lower level patterns, perceptrons are probably going to be detecting vertical lines, horizontal lines, things that compose or don't compose digits. Then here's what I can do. Suppose I train this network, then I throw away the upper portion, just keep that first layer of perceptrons. And so I have something like this. So let's say I have a perceptron which is looking for this pattern, right? And the perceptron fires. What can I say about the input?
That it is exceeding the threshold of.
That it has that pattern. You can say that, can I not? So now I can start off with an empty template over here, and every time that perceptron fires, I'm going to fill in the exact same pattern out here. What do I mean by filling in that pattern? I'm basically filling in the pattern represented by the weights. Correct? So every time a neuron fires, I just put that weight pattern back together. So if I recompose all of these weight patterns, would you expect the outputs to now look like the inputs?
Somewhat, yes.
Somewhat or fully?
As long as your patterns.
Yes, yeah. What is it? What is it, Josh?
As long as your patterns are comprehensive enough to cover all the cases.
But this was a classifier trained to for digits, right? And so the patterns, you're only going to represent those patterns which relate to making classification of whether this is a digit or not. So it's going to reconstruct all portions of the input that distinctly separate or determine whether it's a digit or not. You're going to lose some of the rest of the stuff. But the point is that it's capturing patterns, and you can put those patterns back together to recompose the input. And so I can formalize this, right? In this problem, the network is optimized to recognize digits. It only retains distinctly digit-like or obviously not digit-like features. The rest are irrelevant and will be lost. But then I can try to make this explicit. I can say, recompose these guys such that the output looks exactly like the input. And in which case, I'm going to be learning my network to minimize the error between the output and the input. And learning my network in that manner basically means that all of my neurons are now going to learn features that when put together will compose the input. And if you train them properly, each of them is going to learn a feature which is kind of not like the other features, right? So, or detect features. Is that making sense to everybody? Right. Now, this is what we will call an autoencoder. It's encoding an input back to itself. The simplest autoencoder just has one hidden neuron, right? If I have something of this kind, what will that one neuron learn? Now, to simplify it, I'm going to assume that that one neuron has a linear activation, meaning you're computing a Z and then putting things back together, right? So the activation function is an identity function. If this neuron has an identity activation function, what would it learn? Pardon me? Not quite. here's what you're doing, right? If this is an identity activation, then this neuron is computing WX, going outside because you're recomposing it, it's W trans, you're multiplying that WX by W transpose, right? And so the reconstruction is going to be W transpose times W times X. And if I train this to minimize the error, it's going to be the error between X and W transpose WX, the squared norm, right? And I minimize this over a collection of training data. What am I learning? This is just principal component analysis, right? If the data are zero mean, otherwise it's going to be the Cardin and Loeb bases, but let's assume the data are zero mean for convenience. This is just going to be computing the principal component, the direction in which most of the information about the data lies, the one direction, right? Now, but there's something special about this guy. What if I look at the distribution of all of the outputs, what will it look like? Will it cover the entire space? No, what would it cover? It's going to be just because the output is always going to be of this kind, right? There's an eraser. I've used up my board space. So the output is W transpose WX. This is some scalar. It doesn't matter what it is. And so the output always has the form WS, where S is a scalar. And so in my space, W is a vector. All I'm doing is scaling it by different amounts. So regardless of the input, the data is always going to lie on this line. And what the minimization does is to find the line on which most of the data, I make the least average error. That making sense, right? And so if you got some data and then you've just trained this single component autoencoder with a linear activation, again, the activation is linear, you're going to find the direction of maximum energy. If the data are zero mean, then it's going to find the direction of maximum variance because the two are the same in this case. And all input vectors are going to get mapped onto a point on this line. It doesn't matter what you give me as input, the output is going to be on that line, right? And so suppose I just took the upper portion of this network. Anything I give it, any input is going to lie on that, it's going to result in an output that lies on that line, right? And so I don't even need to have the same, because of this characteristic, right? That the output is always going to be on the line regardless of the input. I don't even need the output weights to be the transpose of the inputs weights. I can have two completely independent sets of weights, but you're still going to learn the principal component direction, and specifically the weights of the output side. They are going to represent the direction of principal components, the principal direction, right? Is that making sense to everybody? Yeah. And if I have more than one weight, one neuron, if I have a bunch of neurons, the output is still going to be of the form W transpose Z, right? Where Z is the output of the hidden layer. And W transpose Z is going to be a plane, the plane that's spanned by the set of weights, right? And so instead of a line, depending on how many neurons I have, the plane is going, the dimensionality of the plane is going to, or hyperplane is going to be the number of neurons I have in my hidden layer. And regardless of the input, the output is always going to lie on that hyperplane. And so this output layer is going to be my principal subspace. In other words, if I just had an autoencoder where all the activations were just linear, and I just trained my network on a whole bunch of data, it's going to learn that the reconstruction side is going to learn the principal subspace, and the entire autoencoder is going to take all the data and map them down to my principal subspace. Okay, time's up, guys, because of her phone beeped. Does somebody on Zoom want to answer the first question? There, you better. Zoom? Nobody on Zoom.
True.
Okay. Thank you. You have 2 people on Zoom. And all right, Vinay, what about the second one? An autoencoder with a linear activation in the hidden layer performs principal component analysis. With linear activations in the hidden layer that has been trained on some data, can only output data on the principal subspace. It's what we said, right? Regardless of the input, the output is going to lie on that hyperplane. Now, everybody with me so far? This is where a little bit of magic happens, right? I'm going to throw in some terminology. The input side, where it creates this hidden representation, I'm going to call it the encoder. And everything on the outside that reconstructs the input from the output of the neurons, I'm going to call it the decoder. So the encoder is the analysis net which computes the hidden representation. The decoder is the synthesizer which recomposes the data from the hidden representation. And now on the decoder side, let me say that I actually have more than one layer and I throw in some non-linearities. What do non-linearities do to a plane? We already saw this over here, right? If I had some plane over here and I threw in a non-linearity, it warped the plane. It bent it, correct? And so when I have a network of this kind and I have non-linearities on the decoder side, this is going to take whatever input you get from the hidden layer and it's going to reconstruct data, but it's going to reconstruct data that lie not on a plane, but on some crazy surface. Because the non-linearities fold the plane, right? And so when the hidden layers have nonlinear activation, this is still going to perform principal component analysis. It's going, because you're trying to reconstruct the input, remember? And because you're trying to reconstruct the input, it's going to try to find a surface such that most of the data lie very close to the surface. This autoencoder ends up performing nonlinear principal component analysis, right? And the best part is, and so I can capture more, because if I don't really know what the data, the scatter of the data is like, I can make my decoder side, I can make the network, the encoder and decoder deeper, wider, whatever, throw in more nonlinearities and capture more and more nonlinear manifolds that sort of capture the structure of the data. And so here are some examples. This was now there are a couple of things over here. The first is we have some data that are flying close to a spiral. And we built a network which has the architecture of the network is given on the slide. It brings it down to one component and then takes it back to 2 components. What would you expect that one component to capture and what would you expect the decoder to capture? You'd expect the decoder to capture a spiral and the hidden, the output of the one component value to capture a position on the spiral. And that's indeed what it captures. If I just plot the output of the network, the output of the network looks like the figure to the right. Now there's some crazy stuff going on. In the ideal world, the network would learn the real structure of the data, which means that now if I take the decoder portion of the network and I feed it z's going from 0 to infinity, it should keep constructing a spiral, right? No, it's just interested in fitting the training data. And so what happened over here is that in this region, it found no training data. So as I kept increasing the z's, once I trained the network, I got rid of the encoder, and then I fed it a series of z's going from 0 to infinity. I find that it initially sort of follows this curve, but then in this region, there was some gap in the training data. I just hopped over to this side and then came back this way and then hopped out and came out. And so you can see that it doesn't do what you think would be intuitive, although it does capture the structure of the data. It also doesn't generalize. So on my training data, I ran out of z's right here. If I keep giving in z values outside of what I saw in the training data, it doesn't continue to compose a spiral. It goes out a bit and goes off somewhere else. So the network captures the structure of the data, but only within the training data itself that it has been provided, and that ends up being an issue. Right? Here's another example where we have a sinusoid, data along a sinusoid, and you can see how as I change the z's, it actually reconstructs the sinusoid, but when the z goes outside the training range, it doesn't continue a sinusoid, computing a sinusoid, it goes off linearly. But then again, you see that this structure can actually capture the shape of the manifold that the data lie on. And this is beautiful, right? This is the autoencoder. When the hidden representation is of a lower dimensionality than the input, this is often called a bottleneck network. This is what was nonlinear PCA. It learns the manifold of the training data. And this makes it particularly useful because the decoder over here can now only generate data on this manifold. We saw this, right? If I didn't have nonlinearities, it can only generate data on the plane. If I have nonlinearities, if it learns something like the sinusoid, it doesn't matter what what input I give the network, it's going to give me something on this sinusoidal curve. If I just take the decoder side of it, the decoder basically captures the shape of this surface. It's only going to generate data on this surface. And so it means that if I train my autoencoder properly, the autoencoder is actually going to capture the surface, the kind of layout of of my data. And now, regardless of what input I give the decoder, it's going to generate some output which kind of lies on the layout of the data, which might be realistic. This is where this is the basic principle that a lot of our generative AI works on. And so if I train my autoencoder on a whole bunch of digits, then the decoder ends up becoming a digit-specific dictionary. Regardless of what I give it as an input, it's going to produce something that lies on the manifold on which digits lie. It's going to look something like a digit, right? Or now, here's where I have to begin praying that this actually works. This was, let me see if this works. It doesn't. Can I have some help, please? I need some audio. Let me check. Can you check if it's there? So what we did over here was to train the autoencoder on examples from a saxophone. Lots of examples from a saxophone. And then once you train it on lots of examples from a saxophone, you throw away the encoder, and then you feed the, nobody there? Yeah. Nope. I think something has to be done here. Bear with me, guys. This will take a minute. It's not just the audio. It's not piping the audio. Okay, something happened. Right? It doesn't like it. Okay, that wasn't it. It actually plays proper notes. But the crazy thing is that if I just feed it any odd input, different inputs result in different outputs, but each of them sounds like a saxophone note. So I actually learned, just by training it on saxophone notes, I end up getting a saxophone dictionary. Now, beyond this, I'm actually going to require you to use your imagination widely because the audio is not playing. Just trust me, right? So this one was a clarinet. You clearly heard a long 5-second note, right? So depending on, again, the kind of input you give it, you hear clarinet notes, yeah.
So in the case of that spiral, where we are trying to project it down to that, or maybe in the encoder phase, won't 2 points in the spiral have the same particular point? How is it?
Meaning?
How is it capturing the positional data of that particular point? Maybe 2 points can have the same point on the
I'm not clear I understand this.
So if you have a principal component and you're trying to project
It's a principal manifold over here.
Yeah, so in that particular point should be projected onto that.
So over here, so yeah, I mean, there's noise, right? You can have multiple points which project onto the same point on the spiral. That's fine. That's what PCA does, right? The points are not guaranteed to be unique. So here's how actually, while you deal with this one poll, I'll try to find out why this audio is not working. You can see the poll. Okay, I get some audio. You didn't see the answers. Done, Harini? That was quick. Okay. So going by the fastest person in the class, is the first statement true? Second?
Yes.
Third? Third?
Yes.
Fourth?
Yes.
Okay. An autoencoder with nonlinear activation performs nonlinear principal component analysis. It finds the principal manifold, which may not be a linear surface, near which the training data lie. And the decoder can only generate data that lie on the principal manifold, right? So the decoder you can think of as a dictionary that can compose data that look like your training data. And I'm basically done, but I'm going to show you a cute app, signal apply separation. This is something that you can do in 5 minutes in your fun time, right? So you're given a mixed sound from multiple sources. You want to separate the sources. So the common technique is a dictionary-based technique. Let's say I want to separate out guitar sounds from drum sounds. Then what I would do is to create some kind of a dictionary that can only generate guitar sounds. And then I would create another dictionary which can only generate drum sounds. And then when I get my mixed recording, I'm going to try to see what should the guitar dictionary generate and what should the drum dictionary generate, so that when these two are added up, they sound like this mixed recording that I hear. If I can find that combination, then the portion that the guitar dictionary generated is going to sound like the guitar. The stuff that the drum dictionary generated is going to sound like the drum. And in our case, we're going to learn dictionaries, except that our dictionaries are autoencoders. So I can just throw a whole lot of guitar sounds into my autoencoder. And now the decoder is a dictionary, right? After training the network, I can throw away the lower portion. And the upper portion is going to be a dictionary for guitars. Similarly, I can use a whole bunch of drum sounds, train an autoencoder, throw away the lower portion. The upper portion is the decoder for drums. Yes, Ranj.
But what do you mean by throwing away the encoder? Because isn't the decoder
Yeah. Now I'm just going to retain that. So basically, all I'm doing is I'm saying that the upper portion, now if I train this well, the decoder portion can only generate guitar-like sounds. We saw that in the putative example that I tried to play, right?
Right.
So
by throwing away, do you mean like just not training it anymore?
No, I just delete that portion of the network, right?
But the decoder uses from the encoding.
Correct.
Encode. So like,
but at this point, my decoder is guaranteed to not, regardless of what input I give it at this point, anything it generates is going to be something like a guitar sound, right?
Right, but in terms of just like the thing about the manifold that it has to be on.
So the decoder is going to generate stuff only on that manifold, right? That's all I'm using. I'm not using anything more, yes.
So, Professor, does it necessarily have to be that the decoder-encoder architectures also always have to be like a conical structure, and then
you want to have some kind of dimensionality reduction? You basically, I mean, not necessarily. The whole point is that autoencoding is the magic. The rest of it is kind of open, really. There are many things you can do. But then here's what I can do, right? If I've trained my guitar dictionary and I've trained my drums dictionary, basically I've trained a guitar autoencoder, and then I deleted the encoder portion of the guitar or AE. So the decoder now can only generate guitar-like sounds regardless of the input. Same thing for the drums. I'm going to sum their outputs. I'm going to compare the output of the sum to my mixed sound, and the difference is an error that I'm going to back propagate. But here's what I do. I use the back propagation to estimate the inputs to the decoder. I'm not modifying the network anymore. I'm using back propagation to determine the inputs to the network. What are the inputs? What must the inputs be such that these outputs, when summed, sound like my mixed signal? And then after that, each side by itself with those inputs must be the separated sounds, right? Let's see if this works. This is trivial, right? Nothing particularly complicated. So I'm hoping this works. Audio is always. There's a wind instrument and a string instrument. Somewhere in there you had this other sound. You may not have heard it the first time around, right? But it actually pulls it out. And you're not doing anything particularly magical. You're just using the physical properties, the geometry of data, right? Really cool. So anyway, I'll stop right here. The story for the day: classification networks learn to predict a posteriori probabilities of classes. The network until the final layer is a feature extractor that converts the data to linearly separable features. The final layer is a classifier that operates on them. Neural networks can also be used to perform linear or nonlinear principal component analysis, and can be used to compose constructive dictionaries, which can be used to generate data, which are becoming all the rage these days. But both the encoder and the decoder sides are important. The encoder learns to extract useful features. The decoder learns to just construct data from that source. And there are many applications for it. Stop right here. Thanks.
That was the first and last time.